Assalamu alaikum and hello. Today we are going to present about flow through ducts and fluid mechanics. Firstly, our group members are Muhammad Riza, Muhammad Noor Ashraf, Muhammad Yusri Izani, and me myself, Muhammad Ashraf Arhan.
Assalamu alaikum and hi, my name is Muhammad Noor Ashraf. So I will explaining about the introduction of this project. Whether a fluid is made to flow over a wall or through a medium determine whether it is considered external or internal. The features of internal and exterior flow are different. When we talk about flow through Dutch, we are talking about internal flow, where the fluid is totally stuffed inside the Dutch. Fluid distribution networks and heating and cooling application frequently involve liquid or gas movement through pipe or Dutch. In such circumstance, a fan or pump is typically used to compel the fluid to flow through a flow section. We concentrate on friction because pressure drop and heat loss during flow through pipes and Dutch are closely related to it. The required amount of pumping power is determined using the pressure drop. For flow section, the words pipe, Dutch, and conduit are frequently used interchangeably. In general, non-circular cross-section flow section are referred to as Dutch, while circular cross-section flow section are referred to as pipe, particularly when the fluid is a fluid, especially when the fluid is a gas. Small diameter pipes are frequently called as a tube.
Next theory, simple theory of flow in a band. In this experiment, we investigate the flow around a 90-degree band in a duct of rectangular section, using pressure tapping along the walls to establish the pressure distribution. Figure above indicate flow approaching a band with a uniform velocity. Within the band, we shall assume a free vortex distribution of velocity given by U equal C over R, where U is the streaming velocity at radius from the center of curvature of the band. Dispersion and secondary flow will be neglected. The constancy may be found by applying the equation of continuity as follows, where B is the width of the section of the duct. Substituting for U from equation above and performing the integration leads to the result. So, the velocity distribution is in dimensionless form. The corresponding pressure distribution may be found by assuming that Bernoulli equation may be applied between the upstream section and a section within the band as follows, where P0 is the static pressure upstream and P is the pressure at radius in the band. It is convenient to express P in the form of dimensionless pressure coefficient Cp, where the equation above. From equation above, this may be written as follows, which may be evaluated for any radius by substituting the appropriate value of U over U obtained from equation above. A comparison with measured values of Cp may be made.
So for the explanation part, objective of this assignment, it has been shown that we need to create a Dutch pipe geometry in ANSYS software. We need to analyze heat and flow through the Dutch in the one simulation. Based on the objective, we learn how to identify typical value of Reynolds number for the laminar, transitional, and turbulent regimens of flow in Dutch with a circular cross-section. We also learn how to understand the friction concept applied in pipe flow and obtain the friction factor for different type of flow. We also learn measure the force generated by air moving through a curved rectangular Dutch. We also learn how to test the validity of control value analysis based on the linear momentum principle. So, what is the problem that we need to solve in this simulation? The problem that we need to solve in this simulation is to represent the behavior of fluid flow in terms of pressure, to create the graph element matrix against number of elements, to represent the temperature occur when fluid flow. Lastly, to determine the counterpoint, conserve mass, momentum energy, and the transition dynamics.
The geometry details and dimension details of our model is as shown and listed below.
First, open ANSYS and select Fluid Flow Fluent. Then import geometry from the part that you have done in SolidWorks. After that, select Edit Mesh. On the meshing window, insert sizing and the 4H at the outlet face. Change the duct number of division and set the number of division to 50. Repeat the sizing step at the inlet face. Then click Generate Mesh. Then insert inflation and select the inlet and outlet face as the boundary. After clicking Generate Mesh, you can see that the mesh pattern has changed. Now, expand the Quality tab and change Mesh Metric to Skewness. Then we can see a Mesh Metric graph has been generated. We can see on the Quality tab that the max amount of Mesh Metric did not exceed the target skewness amount. Create name selection for inlet, outlet, and wall. And now, close Mesh window and click Update. Click Edit Setup. Tick double precision and change number processes to 4. Then, perform Mesh Check at Fluent window. Click Units at General Mesh and change temperature unit from Kelvin to Celsius. Now, expand Boundary Condition and Inlet tab and double click Velocity Inlet and change temperature to 16 degrees Celsius and velocity magnitude to 5 mm per second. And then click Apply. Double click Wall and change the temperature to 3 to 30 degrees Celsius and click apply. Now go to initialization tab and click initialize. After that, go to run calculation tab, set number of iteration to 200 and click check case, and after that click calculate. The graph then will be generated. Now minimize the window and click edit on the result window, insert contour, select inlet, outlet and wall as locations and apply. Then pressure contour is shown. To see temperature contour, change the variable to temperature. Then insert volume rendering. Change the variable to temperature. And on render tab, tick apply texture and select white metal texture and apply. The red color is the max temperature of the wall, while in the middle we can see the heat transfer.
So, based on the result, on the left is the graph for number of elements versus element matrix graph. On the pressure contour, we can see that the highest pressure is located on the curvature. This is the temperature volume render. On the temperature volume rendering, we can see that the wall has the highest temperature, and in between the wall, we can see the heat transferring.
Next, relation theory and result. Contour 1 represents the behavior of fluid flow in terms of pressure. The pressure was set at negative 25.3954 Pascal. From the observation, the specimen data shows that pressure of fluid flow is between negative 25.3954 Pascal to 15.3164 Pascal. Contour 2, the graph element matrix again number of element. The element size is default at negative 0.0236 meter. If the elements matrix increase, the number of element also increase. The highest number of element is at 10,015.00. Contour 3 represent the temperature occur when fluid flow into the duct and output flow. The inlet part mostly flow at the same temperature for all surface, which is 289 Kelvin, and the outlet part have various temperature on surface. The temperature between 289 Kelvin to 303 Kelvin. Element of the flow are represented by contour points or line or surface that move rigorously, conserve mass, momentum and energy, and also represent the tension dynamic. The graph show the velocity gradient at the wall surface is visible in the model, but far from the velocity profile has no change in turbulent model. The mixed flow at the exit is observed when the inlet velocity is increased. This is also indicates the velocity and pressure that produced can show the change and distribution of velocity and pressure that occur in a flow duct band.
That is all from us. Thank you so much for watching.